Hi, this is Kumaran. Today we will discuss about 8085 microprocessor block diagram. In previous video we discussed about the pin diagram. If you want, you can refer that video, then come into this, then you will get a clear understanding because it's a sequence. So let's move on to the today's topic, 8085 microprocessor. This is the functional view. It is given by Intel, who developed that 8085 microprocessor. This is for the understanding how the data is flowing internally, how it is working. This is not the physical structure actually. When you cut the IC, you cannot see such a block because IC internally will have only transistors with the physical connections that is not visible to our eyes. So let's start this discussion in a block diagram, or sometimes it is called as architecture also. In this, the external signals are address bus and data bus connected here, through which external memory is connected. The program counter, that is 16-bit register, will provide the address of the next instruction. So that will provide the which instruction the processor has to fetch. That address will be given by that program counter. Through the data lines, the instruction is copied through this way. It is placed on the instruction register first. Instruction register is an 8-bit register. The opcode is stored temporarily in this. Then it is transferred to the instruction decoder. Instruction decoder means it will find out the real meaning of the instruction, which means that the instruction means all are binary numbers. So each and every binary combination will have different meaning. That meaning is identified by instruction decoder, this register. Then it will enable that machine cycle encoding. Machine cycle means what are the functions done by the microprocessor. For example, the microprocessor will do that opcode fetch, that is one machine cycle. Then it will read that memory, that is one machine cycle. Write memory, another machine cycle. Read, write IO devices, that also 2 machine cycle. Finally, it is interrupt acknowledge. So there are 6 machine cycles. So whatever the instruction you are writing, whatever the application program you are writing, microprocessor will repeatedly do this 6 tasks continuously, not in the predefined order. Depends upon your instruction. It will repeat these same 6 functions repeatedly for every instruction. So every instruction will have opcode fetch 1 machine cycle compulsory. The next machine cycle will be based on the meaning of the instruction. For example, we add that add D means A plus D, that is only 1 byte instruction. That instruction is decoded here. It will enable that accumulator register, enable D register, then enable ALU. Both will be added. Result is updated on accumulator, and flag register also gets updated. So for add D means there might be an opcode. The opcode, you can refer the opcode sheet. So that's an 8-bit binary number. So that number, for every 8-bit binary number, will have different meaning. That is identified by instruction decoder and machine cycle encoding. So it is giving the input to the timing and control unit. Timing and control unit is a circuit which is connected with all other blocks in the circuit. So we will look at that. Every register, all the ALE and everything is connected with the timing and control register, because timing and control unit is enabling all other circuits in this. So at what time which has to be enabled. For example, the previous example, add D means it will enable that D register, A register, ALE, flag register, and accumulator again. So all this in a sequence, not at the same time. At time difference it will do this. So that is the function of a timing and control unit. So such a way the instruction is copied from external memory and placed into the instruction register. Instruction decoder will find out the real meaning. Then it is given the input to the timing and control unit. Then the timing and control unit will manage that enabling and disabling the circuits, depends upon the instruction given by the decoding unit. So that's the flow of instruction execution in 85 microprocessor. Then we'll look into that ALU means arithmetic and logic unit. As you know that it is performing that all arithmetic and logic functions. Arithmetic in the sense it will perform here addition, subtraction, increment, decrement, and decimal DAA, decimal arithmetic. So only these four functions it will do. So obviously it is two function only, addition and subtraction. Uh, for ALU function, every time the one operand is accumulator, which is a default operand accumulator. The other operand you can have either any one of these programmable registers. Out of this 8 register you can have any one, or you can have the data from external memory, or you can have data as part of the instruction add immediate. Likewise it will support 3 addressing modes. But one operand is mandatory in accumulator. So that will take one input from accumulator, other input from the register or memory from external or immediate. So both the data will be added on the ALU, then the result is updated back again to accumulator. So that's the meaning of accumulates. It will accumulate the result of the current ALU operation. So the previous data will be erased and the new result will be updated in this. Then the flags also get affected here. Flag means it's the status of ALU result, what the ALU is performing for that. So we will discuss flags in detail next. Then there is a temporary register. It is acting as a buffer, because when we take data from external memory, it will take some time to release. So that will be transferred to temporary, because the arithmetic logic unit, when it is performing arithmetic or logic functions, at the same time two data should be available, so that the temporary register will enable. This is the system resource register, not available for the user. That's why there is no name is given for this register. Now then we have programmable registers BC, DE, HL. So 6 8-bit registers are available. If you want, you can use as 8-bit, otherwise we can use as a 16-bit register pair also. Register pair BC, DE, HL. So when it comes to the register pair, we will use only the first letter of the register pair. For example, BC means we will use B, HL means we will use H as a general purpose. Then the special meaning of HL, it's a HL pointer. Sometimes it is called the memory pointer. So that's the special use of HL. There is an instruction in 85 to perform 16-bit addition. Even though the 85 is a 8-bit microprocessor, ALU have 8-bit size only, but we can perform 16-bit addition, double addition, DAD register pair, DAD with B or D. So that time the HL will act as accumulator. HL pointer, HL content plus BC content, both will be added. Result is updated on HL. So that's the meaning of DAD register. DAD instruction, which is only 16-bit instruction supported by 86. So DAD B. When it comes to the instruction set, we will go in detail. Then we have two 16-bit registers, stack pointer and program counter. As we started with the program counter, which will auto increment every time to point out next instruction. That is the base of sequential. Automatically it will fetch further. So that is done by program counter. It is increment, automatically it will increment based on incrementer decrementer latch. So it will increment. So then from that new address only the next instruction is copied and placed into the instruction register. So program counter is finding out the next instruction to be executed by the microprocessor. Then we have a stack pointer, another 16-bit register. We know that the stack means it is one-way pipeline. It's first in last out, or you can call it as a last in first out. Suppose your pipe is there, if you are putting bricks here one by one, so whatever you put last, that you have to take first. So when you put in this order, you have to take in a reverse order. So this logic is called stack. So some memory also allocated like this. Some part of the external memory is allocated for stack. that the top of the stack is maintained by stack pointer. So whenever you push any register content, that time the data is stored and the stack is getting decremented once. The stack pointer is decremented once. Suppose you are taking data, that time they get the value and decrement, store the increment and store, get the value and decrement. So these two functions can be done by push and pop instructions. We know that push and pop instructions available in 85. Then we have a serial control. Serial control means it is 85 supported for serial data transmission. For that we need to have serial in data and serial out data, two hardware pins. Through that the external devices are connected, by which microprocessor is communicating binary numbers at a time. Single bit is transmitted or received. Then the parallel to serial to parallel conversion is happening in this block, because processor is handling a data as a 8-bit chunk, but we need to convert from parallel to serial while transmitting. For receiving, again we have to convert serial to parallel. So that's the function is done by serial IO control. Then we have an interrupt control block. Interrupt control means, you know that interrupt, it's an effective way of handling IO devices. Some devices we will connect as an interrupt. Whenever device making a request, the processor will stop the current task, come to the instruction interrupt, execute the program related to the interrupting device, and then it will comes to its main task. So that's the interrupt. In 85 it will support 5 hardware interrupts: INTR, or restart, 5.5, 6.5, 7.5, and drop. So the 5 interrupts out of drop is a non-maskable. Non-maskable in the sense we cannot disable this. That is non-maskable, not able to disable. The remaining 4 interrupts we can disable. One acknowledgement signal. Whenever device making a request, if processor accepts that interrupt, it will acknowledge. Then only that device will remove their interrupt request. RST means a restart. So here the interrupt control function is to validate the interrupt, whether it is enabled or disabled. If it is enabled, to find out the address, vector address, then the control has to be transferred to the new memory address where the program located for the corresponding device making the request through an interrupt. So which is the interrupt control. Then we have timing and control unit. Here the signals are power supply and frequency. You know that the power supply 5 volt is enough to operate the device because of it's a TTL device. Then X1, X2 we will connect external crystal. We have internal divide by 2 circuit. Operating frequency is divided whatever the crystal we are connecting here. Then we have a clock out. The operating frequency is available to the external peripherals which is connected in the system. Then the ready is the signal which will be used as acknowledgement from external slow peripherals. Whenever the processor wants to communicate with that, it is waiting for the ready from the slow peripherals. Then the processor initiate the data transactions. Then the control signals ALE, read, write, all we discussed in pin diagram. S0, S1 are the status signals. IO bar, M bar also status. So we can have what processor currently doing. By reading these 2 signals we can enable. Then the hold acknowledge are DMA signals, direct memory access. You know that direct memory access useful while high-speed data transaction between IO and memory directly without a CPU intervention. Then the reset, whenever you reset in the entire register content, ALU, flag register, accumulator, everything will get erased. Then it will start from the first memory location, it will fetch. Program counter will be 0, then it will fetch from the 0 memory location. That's the first. Reset out, whenever we reset in, it will reset out a signal to reset the remaining peripherals in the system. That is block diagram. Such a way, if it is asked about block diagram or architecture, draw the diagram neatly, then explain each and every block like ALU, instruction register, programmable register, like you can explain. That will serve the purpose. Then the programmable registers, what are available here? The same thing, it is called as a programmer's model. Programmer's model means whatever the register available for the programmer to use while executing instructions, writing programs. So you know that accumulator is a 1 8-bit register which is available always for arithmetic and logic functions. We have a 8-bit flag register, only 5 flags are implemented here. Then we have BC, DE, HL or 8-bit registers. You can use 8-bit or you can use as a 16-bit pair BC, DE or HL. HL special function is as 16-bit addition it will be used. At the same time, it is used as memory pointer also. Whenever we use indirect addressing M, that time the HL will provide the memory address, the data will be copied from that address. Stack pointer and program counter to 16-bit register, the specific purpose we can use it. Then the data lines are always bidirectional, address lines are unidirectional, which is 16 address lines, 8 data lines. So that's the programmer's model in 85 microprocessor. When it comes to the flag register, it's a 8-bit, but only 5 flags are implemented: sign, 0, auxiliary carry, parity and carry. So for example, we will take two data, DA, this data for example which is available on accumulator, then the BB is another register which is available on a D register. So when you write instruction add D, so add D means, so it will add A plus D and the result will be sum is stored on accumulator, then the flags gets affected. Let's have D means it is 1101, A means 1010, B is 1011, that's we return. So when we add 2-bit binary number here, 0 plus 1 is 1, 1 plus 1 is 10, 1 plus 1 is 10, 1 is carried here, 0 here, 111 is 11, so 1, 1 plus 1 is 10, 1 plus 1 is 10, then 1 here, 111 is 11. So here we added that two 8-bit numbers, we are getting a 9th bit, that bit is called that carry. So if you are adding two n-bit numbers, the n-bit 1 plus answer you may expect that the n plus 1th bit is called carry here. And the sign is to represent a number is negative or positive. So the first bit is dedicated for sign. So this bit is called sign here on the sum value. So this is sign, 1 means negative, 0 means positive, but here whatever it reflects here, that is reflected on the sign flag. That's the thing. Then we have auxiliary carry. Auxiliary carry means the carry occurred from lower nibble to higher nibble. Nibble means 4 bits, lower 4 bits to the higher 4 bits. If it is carry occurred either 0 or 1, that is called auxiliary carry. This will be used on performing decimal arithmetic. Then we have a parity. Parity means number of logic 1 present in the sum value alone. Yeah. In the sum we have even parity. This device is even parity device. So number of logic 1s is even means the bit will be 1, else it is 0. In this case it is even number of 1s, so the parity flag will set to 1. 0 flag is if the entire the sum all 8 bits are 0, then only flag will be set to 1, else it will be 0. In this case we have some value, so the 0 flag is 0 here. So here carry is 1, sign is 1, auxiliary carry 1, parity 1, 0 is 0 because we have some answer in this. Likewise we can write any other take any other input, we can find out carry. So that's all about architecture of 8051 or flag register. I hope it is clear. If you have any doubt or clarification, you can ask in comments. I will respond. Thank you for the patience.